Hello students, so once again I welcome you. So now we are going to see the next experiment in our thermal lab, that is wall timing diagram in 4-stroke CA engine. CA engine means compression ignition engine. Okay. So here we are having the theoretical wall timing diagram and actual wall timing diagram. In theoretical wall timing diagram, the wall opening and closing will be exactly at the center, that is dead centers. We will be seeing at top dead center and bottom dead center. We know what is top and bottom dead centers. Okay. So first process in the cycle is suction followed by compression, then power, then finally you will be having the exhaust stroke. So all these stroke will be happening in the separate processes. So only it is called as 4-stroke diesel engine. Okay. Actually, the valve opening and closing is not sudden. It happens gradually. So for that reason only we are going for the actual valve timing diagram. So this is the diagrammatic representation for actual valve timing diagram. Here you can see the inlet valve open will be before TDC. So why? Because at this part only maximum amount of air will enter into our engine. Then similarly you can see the inlet valve close after BDC. This is because due to inertia more amount of air will be entering into the engine. Okay. Then when you see the exhaust valve open, it is supposed to happen at this center, but it is happening at this point 45 degree nearly. So why? So because to reduce the piston pressure, the exhaust valve open is before BDC. Then finally, if you see the exhaust valve close, which is after TDC, this is to enhance the process called as scavenging, through which the already burnt exhaust gases will be removed from the engine due to the fresh entry of the fresh air. So this is how the actual valve timing diagram will work. Okay. So in the engine, the next we will be seeing the experiment. There you are supposed to measure the circumference of the flywheel, through which only we are going to estimate the angles. At what angle then valves will open and close. For that there is a conversion for circumferential length to angle. For that you need a formula that is called as pi d, which is nothing but the circumference of the flywheel, which is equal to 360 degree. Now for particular arc length L, what will be the theta, which is equal to, you just cross multiply 360 into L divided by pi d. It will directly give the angle. Okay. Once you measure the circumferential length, directly substitute over this here in this formula, thereby you can able to find the angle. After finding the angle, substitute this angle over the points wherever it is required and draw the actual valve timing diagram. Okay. Why we are going for this valve timing diagram? The reason is to execute the proper functioning of each process and thereby increasing the efficiency of the engine. We are going for this actual valve timing diagram. Come, let's see how to take the experiment. So this is the cut section view of the 4-stroke CA engine. Now I am going to rotate the flywheel so that our piston will move upwards. So see, my piston is moving upward. So the point where the piston reaches the topmost position, that point is called as TDC, which you have to mark in the flywheel. Okay. So this is the point where the piston has reached the TDC. So I am marking it as TDC. Further movement, the piston will move downward. The bottommost position reached by the piston is called as BDC, which will also has to be marked in the flywheel. So this is the pointer. So here I am marking it as BDC. Now we have to identify the process, at which process the piston is in. For that you have to check the valves. This is inlet valve as it is connected to the air filter. Now inside we can able to find another wall that is called as outlet wall, which will be connected to the silencer. Okay. Now, if I move my flywheel in the clockwise direction, the piston will move from TDC to BDC. Now the suction process will take place. At that time the inlet valve will open. So the piston is going downward, so air from the outlet will enter into our cylinder. So when on further movement the piston will reach BDC, then once again it goes upward. While going upward, both the valves will be in the closed position. So this is called as compression. If the valves are closed only, the air inside the cylinder will be get compressed. Okay. At the end of compression, you will be getting the injector. Injected diesel will be into the compressed air. So this will leads to power stroke. Okay. Now the power stroke is taking place as the piston is moving downward. Now once the power stroke got ended, the exhaust valve will open. Now you can able to see the exhaust valve is opening. So now exhaust stroke will takes place. Okay. At the end of exhaust stroke, you will be having the inlet valve opening. So this is called as scavenging period. At this time, both the inlet valve and exhaust valve will be at the open position. This is the process of IC engine. So in the flywheel, I have obtained my actual valve opening and closing near my dead centers. So near the TDC, I have obtained my exhaust valve open. Similarly, exhaust valve close. Similarly, I have obtained my exhaust valve open near BDC and inlet valve close after BDC. Now what I am going to do is, I am going to use a measuring tape for measuring the circumferential length from the nearest dead center. For example, from BDC, I am measuring the circumferential length of exhaust valve open. So this is nearly 10 centimeter. So similarly, you have to measure for each and every valve opening and closing. After taking the measurement, you have to enter in the approximate column. Then using the formula what I have discussed earlier, you have to convert the circumferential distance into angle. So by this we can able to draw the actual valve timing diagram. So there is a graph called polar graph. So in which we will be marking the values what we have obtained as inlet valve open, close, then exhaust valve open and close, and finally we will be getting the output as like this. So this is the valve timing diagram.